So, now let us start with the one more example for illustrating the simplex algorithm. Suppose you have a function like this, maximize z equals x1 plus x2 plus 3x3 subject to these two constants. So, again if you see the constants are of less than equals type, that means I have to introduce slack variables to make it the equality sign. So, if I am writing it in standard form, I can write it as maximize z equals x1 plus x2 plus x3. I will come to other variables subject to 3x1 plus 2x2 plus x3 plus x4. Here x4 is the slack variable and this is equals to 3. The next one is 2x1 plus x2 plus 2x3, x4 component is not there, 0 into x4 plus x5 equals 2. So, here I can write it as 0 into x5 always. So, x4 is the slack variable associated to the constant 1, x5 is the slack variable associated with the constant 2. Now, as I have mentioned earlier, the coefficient of the slack variables in the objective function always will be 0. Please note this one. Earlier also I have told it that the associated cost, the coefficient of the slack variable in the objective function will be this one. So, it is 0 into x4 plus 0 into x5. Now, you see which one first you have to decide. Of course, x1, x2, x3, x4 and x5 all are greater than equals 0. So, please note this thing, these all are greater than equals 0. So, what I have to decide now? What should be the basic variables in the basis? So, just like earlier, which portion of these two equations are forming a unit matrix? Here if you see again these two, if I take, that is coefficient of x4 and x5 in both the equations, if I take, it is forming one unit matrix. And so, therefore, these variables x4 and x5 will enter into the basis. So, xb will be x4 and x5. So, B you can write down A4 and A5. As I mentioned earlier, again we are stating your Cj, this value is nothing but the coefficient of the variables given in the objective function. That is, here coefficient of x1 is 1, x2 is 1 and x3 is, sorry, this will be 3x3. It is 3x3. Coefficient of x4 is 0 and x5 is 0, because they are the slack variables. So, I can write it as 1, 1, 3, 0 and 0. So, what would be the corresponding values of Cb? This is again nothing but the coefficient of x4 and x5 in Cj. So, that means it will be 0 and 0. B values are these two values for the right hand side of the equations. So, this is 3, 2. Now, you just write down the coefficients corresponding to the variables, that is 3, 2, 1, 1 and 0, and this one next one will be 2, 1, 2, 0, 1. So, you are just writing the variables. Now, you have to find out what are the entering variable, what is the departing variable. For that one, first I have to calculate Zj minus Cj. Zj minus Cj is, sorry, this is not 0, your A4 is 0, right, both are 0. So, the value of this one, value of Zj minus Cj for this column, first column will be Cb into Xb, that is 0 into 3 plus 0 into 2 minus Cj, which we have written, and this is equals to minus 1. For this case again this is minus 1. For this case 0 plus 0 minus 3, this is minus 3, this is 0 and this is 0. So, which one will be the entering vector for which Zj minus Cj is most negative? For this case, the third column gives you the most negative, that is minus 3 corresponding to the variable x 3. So, your entering vector will be this one. So, this is the entering vector, and now I have to calculate what would be the outgoing vector. To calculate outgoing vector, I have to find out the ratio of x b r by y r j, that is here. What is that one? As I have told, b by x j, whatever column you are choosing. So, in this case it is 3 divided by 1, b by, again I am writing b by this x j corresponding to this. So, first one is 3 by 1, second one is 2 by 2. So, the first one value is 3, second value is 1. So, the minimum value of these two is 1. So, your outgoing vector will be this one. So, your outgoing vector is x 5. So, outgoing vector is x 5 and x 3 will enter into the basis. And what is the pivot element? The pivot element is the intersection of the lines, column and the row corresponding to entering vector and outgoing vector. So, this is the column for entering vector and this is the row for outgoing vector. So, the pivot element will be this one. Since pivot element is this, in the next table what I have to do? I have to make this one as 1 and this all other elements of this one as 0. So, I have to do it now. So, in the next table what I will do is that firstly Cj values will remain same, that is 1 1 3 0 0. Your variables will be x 4 and since x 5 is going out. So, x 5 will be replaced by x 3 variable. So, here it will be x 4 and x 3. So, it is a 4 and a 3. So, the values corresponding to these are x 4, coefficient in the cost function it is 0, corresponding to x 3 it is 3. Now, what I have to do? In these columns, first I have to make this element as 1. That means, each and every element of this row including b, I will divide by 2. So, that this element will become 1. So, that it becomes 1 1 1 by 2 1 0 1 by 2. So, by dividing by 2, since this is the pivot element, I have to make it 1 and all other elements of this column I have to make it as 0. So, once I am doing it, I will obtain the result as 1 1 half 1 0 and half, right. So, by doing this, now to make it this column, this element as 0, I have to make this first row minus second row divided by 2, first row minus second row divided by 2. So, that the value in this case first row minus second row divided by 2. So, 3 minus 2 by 2. So, it will be 1, 3 minus 1. So, this b value will be this, and then all others if I calculate in the same fashion from here, that first row minus 2, second row divided by 2, I will obtain this is 2, x 1 will be 2, this is 3 by 2, 0, 1 and minus half. Now, again like previous time, we have to calculate the value of the reduced cost value, that is Zj minus Cj. For the first case, it is 0 into 2 plus 3 into 1 minus 1. That means, 3 minus 1, this is 2. Similarly, for the second case it will be half. For the third case, third column 3 minus 3 it is 0. For this one 0, 0 minus 0 it will be 0, and for this case it is 3 by 2, this is 0 minus 0. So, this is 3 by 2. So, once I am getting this, I am finding that Zj minus Cj is greater than equals 0. So, optimum solution has been achieved. Since Zj minus Cj is greater than equals 0 for all j, so the optimum value has been achieved and I do not have to go for the further iterations. So, what is the optimum solution now? If you see in the basis in the last table, one slack variable is also there, that is you have only one decision variable x 3 is there. So, since only x 3 is there, all other values of the variables will be 0, that is x 1 equals 0, x 2 equals 0 and x 3 this is equals to 1, and the value of z max again you can calculate from here. Value of z max, obviously this into this plus this into this. So, the value of z max will become 3. So, this is the solution. Again, if you note that for this case also the solution is unique. So, I hope it is clear. Afterwards, we will basically use this formation, this iterative process with some improvement for finding the solution of some other types for the same LPP itself, and we will not discuss in details how from one table by iteration I am obtaining the next table. Now, let us go to the next topics, that is the other one where we call it as big M method. The first one which we have done, that is the simplex method. Now, we are going for the big M method. If you remember, whatever we are doing in the solution of the problem, your constraint take the form a x less than equals b. The form is something like this. We have taken in both the examples the constant inequality is less than equals type, but this may not be the case. You may have certain cases where the value or the constant can be of greater than equals type also. That means, if the constant is a x greater than equals b, then what will happen? If you remember earlier, we told that whenever you have a x greater than equals b, to make it equality type, we are adding the surplus variable, sorry, we are subtracting the surplus variable from here, that is a x minus x n plus 1, this is equals to b. We added this one. So, now what is the coefficient of the surplus variable? Coefficient of the surplus variable always will be negative, that is minus 1, since you have to subtract. So, to obtain the initial basic feasible solution, what we do? We make x 1 0, x 2 0, like that way x n equals 0. So, in that case what will happen, which imply x n plus 1 equals say minus b 1, x n plus 2 equals minus b 2, and like this it will go on. Or if you see the variables x n plus 1, x n plus 2 all are negative variables, but in our LPP we have told that all the variables must be non-negative. So, this is a problem, all the variables has to be negative, but for this case these variables x n plus 1, x n plus 2, these are negative. So, we cannot consider these variables. To overcome this situation, for each surplus variable we add one more variable, which is known as artificial variable. which is known as artificial variable. So, basically whenever you are using a surplus variable, then we are checking that the value of the surplus variables are becoming negative, which is not acceptable. For this reason, for each surplus variable, we attach with them one more variable, or we add one more variable, which is known as artificial variables. So, actually what happens, suppose you have m inequalities of greater than equals type. So, what will happen? You are having n decision variables, this is already there, plus since you are having m greater than equals type variable. So, you have to include m surplus variables, and I have to add, we have told that for each surplus variable I have to add one artificial variable to make this one feasible. So, there will be m artificial variables, so in total you are having n plus m variables. Out of that n decision variables, m surplus variables and m artificial variables. Now, how you will obtain the initial basic feasible solution? Initial basic feasible solutions can be obtained by making n plus m, that is this plus these variables, equals to 0. This n plus m variables equals to 0. So, that you can obtain something like this. Artificial variable a 1 will be equals to b 1, a 2 equals b 2, like that way a m equals b m. You will obtain this thing, a 1, a 2, a m, this will be equals to 0. So, to obtain the initial basic feasible solution, what we are doing? We are making n plus m variables equals to 0. But if you see one thing, the solution of or final solution of this will not be the solution of the original problem, because the original problem and the modified problem after including the artificial variable, they are not same. For that reason, I have to remove somehow the artificial variables from the scenario, that is from the final basis matrix or from the final table. To do this one, what happens? A very high value is attached to each artificial variable as coefficient in the cost function. So, please note that for each artificial variable, a very high value is being attached in the coefficient function. A very large value, or sometimes we call it as penalty, we add as a coefficient. Sometimes we call it as m. So, please note here that whenever you have surplus variable, for surplus variable, the coefficient of the surplus variable in the cost function will be 0. Coefficient of the surplus variable in the cost function will be 0, whereas if you have the artificial variable, in that case the coefficient we are attaching in the cost function is a very high value, which we are calling as capital M. So, how it will look like now? So, in the normal case, whenever you have less than equals type coefficients, in that case you are attaching, you are introducing slack variable to make it the equality type. If you have greater than equals type of equation like this, then you are attaching one slack variable, one surplus variable as well as one artificial variable, and in the cost function For surplus variable, coefficient will be 0, and for artificial variable, a very high value, say m, we are attaching to the cost function. So, your problem would be like this. Suppose I have a problem, maximize z equals C1 x 1 plus C2 x 2 like this way, plus Cn x n subject to a I 1 x 1 plus a I 2 x 2 plus a I n x n, which is greater than equals b I, where I equals 1 to m, that is m constraints are there. So, if this is the case and your x j greater than equals 0, where j equals 1 to n, that is you have n decision variables and m constraints. So, what I have to do here? To make all these m equations as equality, I have to add m artificial variables and m surplus variables. So, your maximize will be z. I am just writing first subject to, then I will write down that part. Subject to a I 1 x 1 plus a I 2 x 2 like this way, plus a I n x n minus x n plus I plus a I. This is equals b I. For each I equals 1 to m, for this variable a I 1 x 1, a I 2 x 2 plus a I n x n, I am subtracting one surplus variable to make it equality, but since the value is negative, so I am adding one artificial variable a I over here, and which is equals to b I. I will take a I in such a fashion that it will go out. So, your maximized function will be C 1 x 1 plus C 2 x 2 plus C n x n plus 0 into x n plus 1 plus 0 into x n plus 2, like this way it will go 0 into x n plus m. These are the coefficients of the surplus variables. Please note this one. These are the coefficients of the surplus variables, which is 0 always, just like slack variables, and minus m into a 1 minus m into a 2, like this way, minus m into a n. So, for each artificial variable a I am attaching a very high value m in the cost function, that is minus m. Your x j greater than equals 0, obviously x j greater than equals 0, j equals 1 to n, n plus 1 and n plus m. A j greater than equals 0, j equals 1 to, like this way, up to m. Basically, why we introduce the concept of artificial variable? If I write down these equations, what you will find that you will not get any unit matrix, because this value is negative. So, you are not obtaining any unit matrix. To make the unit matrix, I have to add one more variable, and somehow I have to get rid of it. And to get rid of this variable, only we have attached the very high value, and simultaneously this gives us the basis also, that is linearly independent set of vectors for this one. So, my problem, whenever I have this greater than equals equality problem, in that case what I am doing, I am attaching both surplus variable as well as the artificial variable with this case. So, what we are doing, please note few things. Artificial variables are fictitious variables. which has no meaning or economic significance. So, these are fictitious variables to manipulate my problem to obtain my solution, but it has neither no physical meaning nor it has any economical significance, but it has great computation convenience. Please note this one, it has some great computation convenience, that is, for computational purpose we have used this artificial variable. The reason for assigning large penalty in the coefficient of the artificial variable in the objective function is that these artificial variables can be removed from simplex table as soon as they become non-basic variables. So, basically we want that these variables should out from the simplex table. For that reason, we have attached a very high value to these particular tables, and for this reason effectively we are using or we are adding a very high penalty to this. The third point is that the simplex algorithm which performs its search for a solution that has greatest objective function value will systematically discard or avoid solutions having positive artificial variables. That is, by default it will attempt to converge to a solution for which a I equals 0. Please note this one, the procedure is such that we will try to converge to a solution where the value of the artificial variables are 0 and they are being discarded from the basis. Now, one point will come here, that is what we are always saying that m will take a very, let me take this one or here, okay, m will take a very large value. What does it mean, very large value? Because whenever I am subtracting something, some element may be greater than m. So, here what assumption is there, whenever I will make or subtract any element, say a from m, my assumption will be m will always be greater than a. That means, whatever larger value of a you take, value of m always will be greater than a. That we have to assume that it takes very large value, or in other sense, if we try to subtract any element from m, always value of m will be greater. So, for manual computation this is really good, there is no problem, but whenever we will try to find out the solution, we will try to write down some algorithm and we will try to implement it in computer, we face certain problem that what kind of value we should supply for m. So, there we face certain problems. For that reason, although this algorithm big M approach is very efficient, but we call sometimes we use some other technique. And please note this one, this modified simplex method, whatever I have discussed here is known as big M method or sometimes people may say it as penalty method also. Sometimes people say it as penalty method. So, this method we call it as big M method or the penalty method. So, just we have discussed, if your inequality is greater than equals type, then by subtracting the surplus variable as well as adding the artificial variable, we are making it equality. The reason for addition of the artificial variable, I think it is clear to you now, to obtain the unit matrix, so that from where we can obtain the basis matrix for that reason, and to discard the artificial variable, we have associated a very high value to this particular, we have associated with the coefficients of these artificial variables a very high value in the cost function. So, in the next class we will see what are the procedures to find the solution of the big M approach, and we will solve certain problems.